Many convergent series have negative terms, alternating, or some other pattern. Taking the absolute value of each term of a convergent series with some negative terms makes the new positive series less likely to converge, since the sum will be greater without negative terms. If the new positive series is still convergent, the original series is called absolutely convergent. If, on the other hand, the new positive series diverges, the original convergent series with negative terms is called conditionally convergent. If a series converges after taking the absolute value of its terms, it is guaranteed to also converge with no absolute value. As a review, if the absolute value series converges, then the series is said to be absolutely convergent. If the original series converges and the absolute value diverges, then the series is said to be conditionally convergent. And if a sub n diverges, then absolute a sub n will diverge as well. Determine whether each of the following series is absolutely convergent, conditionally convergent, or divergent. You may recognize the first example as the alternating harmonic series. That one converges by alternating series test. Let me show you the steps. Because both of these conditions are true, then this series converges by the alternating series test. Now let's consider the absolute value of each of those terms being added together. Negative 1 to the power of n in an absolute value would just be 1. This is the harmonic series, which we know diverges. So the non-absolute value version converged, the absolute value version diverged, therefore this series is conditionally convergent. Now we haven't worked much with series that have cosine or sine in them, so I want us to just plug in n and find the first few terms. Let's think about the signs of each of these terms. Pi halves is where cosine will cross from positive to negative. So cosine of 1 over 1 is a positive value. Cosine of 2 over 4 is a negative value. Cosine of 3 over 9 is also negative. Cosine of 4 over 16, also negative. And the next term after that goes to be positive. So as you can see, this series is not alternating, but is also not fully positive. For the types of examples whose sign changes are not purely alternating, it can be especially helpful to determine if the absolute value of that series converges. I may not know exactly what cosine 1, cosine 2, cosine 3 are, but I do know that cosine of any integer is going to be between negative 1 and 1, because the amplitude of this cosine is 1. Now that we've made cosine n absolute value, whatever is in the numerator will always be positive. Because cosine n is between negative 1 and 1, the absolute value of cosine n will be less than or equal to 1. Because the absolute value of cosine n is going to result in a number between 0 and 1, a great series to compare this to would be the p series 1 over n squared. This converges by p-series test because p equals 2 is greater than 1. The only way this comparison will help is if 1 over n squared is greater than or equal to absolute value cosine n over n squared. Keep in mind that cosine n absolute value is only between 0 and 1. If the absolute value of cosine n is 1, then we have a true statement. If the result is 0, then we also have a true statement. If the numerator happens to be any fraction between 0 and 1, then we still have a true statement. Imagine, cosine n is equal to 1 over 10. Divide that by n squared. That is 1 over 10n squared. Bigger denominator means smaller number. So is this a true statement? Absolutely it is. Making the absolute value of cosine n over n squared from n to infinity a convergent series by direct comparison test. If the absolute value of the original series converges, then the original series is said to be absolutely convergent. Let's take a look at this final series. It's also an alternating series. We can take out that alternating part to see it better. At this point in time, I'm going to use the alternating series test to see if this original series is convergent. This would mean the limit as n approaches infinity of the non-alternating part needs to be equal to 0. But guess what? E to the n grows at a much faster rate than n to the e, so the value of this limit is infinity. Therefore, this original series diverges by alternating series test. Now, if the alternating version of the series diverges, then the absolute value of the series will also definitely diverge. So this series is divergent.